All right, geometry students, so we are starting chapter 11 today, and believe it or not, this is our last chapter of the year, which is pretty exciting. We've made it through a whole year of geometry. So chapter 11 is all about surface area and volume. So it's a pretty fun chapter, I think, and it's very closely related to all of the areas that we worked on when we were in chapter 10. So it'll be hopefully some review. Our topics today are 11.1 and 11.2. 11.1 is about nets, and then 11.2 is about the surface area of prisms and cylinders. So we're talking about nets today, just kind of as an introduction, and then 11.2 is really kind of more the bulk of what our topic is about today. All right, so for our do now, and this will just be kind of short review for you quickly, but just go ahead and find the areas of the shapes and leave that circled on number 3 in terms of pi. So pause here, take a minute, figure out these areas really quickly, and then check your answers with me. All right, I'm going to show you guys the answer, so go ahead and pause if you have not done so yet. On number 1, it's just a rectangle, so we're finding base times height, and that's going to be 12 centimeters squared. On number 2, that's a triangle, so our area is going to be 1/2 base times height, and the base is 12, the height is 14, and so our area will be 84 feet squared. And then on number 3, this is a circle. Make sure that we're finding the radius, right? So the area is pi r squared. The radius there is actually 9. So that would be 81 pi inches squared. Hello, I'm going to pop myself up in the corner here because I have a few things I want to show you guys as we get started on our notes. So our first vocabulary word is a net, and a net is a 2D or a two-dimensional pattern that you can fold to make a 3D figure. Now, I have some really nice nets at school that if I was there, I could show you, but clearly we are not. So I made my own nets to show you, and you can laugh because you're in the privacy of your own home. But they're not as great as the ones I have at school, just full disclosure. So here's an example of a net. Here's one that I have kind of folded or drawn out for you guys and cut out. So a net is two-dimensional, right? It's just like a piece of paper is two-dimensional, right? It's just kind of a flat surface. But when I fold it, I can make a three-dimensional figure. So if you look at this example, this net that I have here, we have a triangle on either end, and then we have this rectangle, and then we have these two rectangles on the sides. So what happens if I start to fold this is I'm going to fold my rectangles up to meet each other, and then I'm going to fold my triangle up so that it sort of matches right along with those sides. And then, again, this is sort of hard to tell because my cutting job was not quite as nice as I would have done at school or the ones I have at school, but it should form kind of this triangular prism, right? Like a long, skinny, triangular looking shape. The other one I have is this one. It looks like it has two circles and then a big rectangle in the middle. Well, if I roll this up, if I roll this little rectangle up and then kind of fold my triangles down, it looks like this little cylinder shape, right? So it's kind of round and it has a little top and a little bottom, but I could just make it into a nice little cylinder there, okay? The last one I have looks like this. It's got 4 triangles and then a little rectangle in the middle. Now, if I put that rectangle flat on the ground, or on my hand in this case, and then fold my 4 triangles up, they should meet to make this nice little pyramid shape. And again, this is not a perfect net because they should all kind of match up together to make a nice pyramid or a nice cylinder or whatever. And mine are not that great. But you can use your imagination. I'd encourage you, if you're having a hard time visualizing it, to just go and look up some maybe YouTube videos or some Khan Academy videos about nets. And yeah, that's all I have for nets for now. All right, so mercifully, you do not need to see my face on this slide, but our next definition is a polyhedron. So actually 2 of the 3 nets that I showed you on the last slide formed polyhedrons. And a polyhedron is a 3-dimensional figure whose faces are polygons, right? So that doesn't include the cylinder with the circles that I showed you. But the first and the last one that had the triangles and the rectangles, those ones are polyhedrons because their faces are polygons. So one example that I showed you was a pyramid that had 1 base, and then a prism was another example that I showed you that had 2 bases. So let's talk about what is a base, right? So I'm going to go ahead and highlight on the pyramid the base in blue. So my base is down here. A lot of people think of the base as just kind of the bottom shape, But what we're going to think of bases as is there's usually either one or two of them, and they have to be identical to each other, right? But you can tell in a pyramid that all of the other parts that are not a base are going to be triangular, right? Because they have to kind of meet up at the top there. So the base of a pyramid is usually going to be a non-triangular shape at kind of the bottom across from this top vertex. And then in a prism, you'll always notice that there is one base that's directly across from an exactly identical congruent base. So you'll see I have a hexagon down here and another hexagon on the top here. A face, our next word, is any polygon that forms a side of the polyhedron. So a face could be the triangle in this pyramid, a face could be the pentagon at the bottom here, right? On the prism, it could be these rectangles that go around the sides, or it could include the hexagon. So a face is just any of the polygons, right, that make up these two polyhedrons. An edge is the segment where the faces meet. So if I was just to kind of outline over here, maybe like this right here is an edge, right? Or even this guy down here is an edge, okay? So those are our edges, and then a vertex is the point where the edges meet. So again, if I was going to start highlighting an edge, I might say that this point right here is a vertex, or this point up here is a vertex. Literally any point where those edges, where those segments are meeting is considered a vertex, right? So it's basically just any pointy part of the pyramid or the prism. And then finally, a lateral face is any non-base face. So that's where we have to kind of specify a face is going to be any of those polygons, but a lateral face, lateral means kind of like around or on the sides. It's going to be any of these triangles, but not including the pentagon, or it could be any of these rectangles over here, but not including the hexagons, right? So it's any face that is not a base. All right, so our next word is a cylinder. And again, a cylinder is very, very similar to a polyhedron. The only difference is that it has two circular bases. So we're not talking about just faces that are polygons anymore. Now we can have circles, which are not technically considered polygons because they have curved sides. So if you look at my cylinder here, right, I have a circular base over here and a circular base over here. Now again, notice that my base is not just the side that's on the bottom of the shape, right? A base could be on the left or on the right or top or bottom or front and left, but they need to be congruent shapes to each other. So here in my cylinder, I have two congruent circular bases. All right, so a bit more vocabulary regarding prisms. And remember that prisms have two bases. They're not a pyramid, right, where it just has one base. So it's a specific type of shape here. The height of a prism is defined as the length of the altitude that joins the bases together. If you're taking notes, you'll want to highlight that phrase, joins the bases, because that tends to be kind of a sticky definition for many students, and I'll show you why in just a moment. And then the bases are defined as two parallel and congruent faces of a prism. And again, if you're taking notes, you might want to highlight that because that tends to be a little bit tricky for students to sort of disconnect from their old notion of a base. So I'm going to show you below two different prisms, and we're going to highlight the bases and the height. So the old sort of definition that many students have in their brain is that the base has to just be whatever sort of shape is on the bottom, right, against the floor of the shape, if you will. But in our specific definition for prisms, it tells us that we have to have two, and they must be parallel and congruent. Well, if I look at this rectangle that's on the kind of bottom of my prism here, there is no other rectangle above it that is parallel to it, and there's no other rectangle that's congruent to it. So that actually rules out this rectangle as a base. And it also rules out the rectangle in the back and this rectangle here in the front because they don't have anything that is parallel and congruent to them. However, there is a triangle right here that has a triangle over here that appears to be parallel and congruent. And since we know that it's a prism, it's told us here, and the rectangles, none of those fit the bill. These triangles must be our bases of this prism. So I'm going to go ahead and highlight those. And then when I talk about the height has to join the bases together. So again, old notion of height is, oh, it must go from the bottom to the top, right? So that it sort of must be this from down here all the way to up here. But now that we know the definition, we know that the height has to go from one base to the other. So I'm going to outline it as being right there. So this shape over here, this prism that I have, again, a lot of students are going to want to look at this base down here and say, oh, that must be the base because it's on the bottom. But it doesn't have another shape that is parallel and congruent to it. It does have this shape up here, this rectangle that is parallel, but it's obviously not congruent. Same thing with these two rectangles that are kind of tilted on the sides here. Those guys appear to be congruent, but they are not parallel, so those aren't going to work. So our only option that's left over actually are these trapezoids that are in the front and the back. I'm just going to outline the edges of them. So the trapezoid in the front and the back actually are our bases there because they are parallel to each other and they are congruent shapes. And then we would say that the height connects those two together. So I'm going to outline that 6-yard number as my height there. Remember, final thing, I just want everyone to get this in their brains, that the height of a prism joins the two bases together. The height joins the two bases together. So the height on that trapezoidal prism was not the height of the trapezoid, it was that 6-foot distance that joined the front trapezoid to the back trapezoid. All right, so a few more definitions here, and I promise we are almost to the end of our definitions. It's the first section of the chapter. But surface area is the total area of all of the faces and curved surfaces of a 3D figure, right? So if it was a polyhedron, we'd look at all of our polygons, and then if it has curved surfaces, right, that would be like if it's a cylinder and has some sort of rounded edges. The lateral area is going to be the sum of the areas of only the lateral faces. So basically the lateral area is finding the surface area but without the bases. So if it was a pyramid, we would take out that single base. If it's a prism, we'll take out the two parallel and congruent bases and just kind of find around the sides. Okay, so in example 1, we're going to find the area of each face. And remember that finding the area of each face is like finding the net, right? Kind of unfolding it so that we have them flattened out and have each of the shapes kind of in a two-dimensional way so that we can find the surface area of each prism. So on number 1, we've got kind of a rectangular looking prism. On number 2, it looks like we've actually got a cylinder, so 2 circular bases. So on example 1, number 1 over here, rather than drawing out an entire net for you, I'm just going to sort of outline each of the different pieces and highlight them as we go. So remember, we're going to have to find all of the different rectangles that go into this prism here. So first I highlighted that there's the top and the bottom area, and that looks like it's 6 by 11. It's just a rectangle, right? So it's going to be 66 kilometers squared. The next piece I found was the front and the back area. So I highlighted those here. So in pink, the front and the back area is going to be 6 by 8. So notice I have an 8 over here, and I just kind of copied that over to here. So the front and back area, each of those pink rectangles is going to be 48 kilometers squared. And then the left and right area, which I've highlighted in blue, I know it's kind of hard to see back there, is going to be 11 by 8, or each of those rectangles will be 88 kilometers squared, right? So by the way, we're doing this kind of the long and the hard way of having to find each individual piece. And then we're gonna have to go through and add them all together. I'll show you the shortcut in just a minute, but we have to do it the long way first. So I'm going to add together the top and the bottom, the front and the back, and the left and the right. So top and bottom are both 66, front and back are both 48, left and right are both 88. And again, I'm just showing you kind of different ways you could show your math. You could multiply them each by 2 and add them together. But when I do all of that math, I end up with a total surface area of 404 kilometers squared. Pretty big prism in kilometers up there. In number 2, I went ahead and drew out the net just because I think it's a little bit easier to visualize when we sort of unfolded it. So notice that we have 2 circles. So I've drawn out my circles here. And then I also have kind of this long outside lateral area. So I'm going to outline this information that I know. I know that I have a 4-kilometer width right here. So I outlined or wrote that in on my width of my rectangle here. And then I know on my circle that I have a radius of 5 kilometers. So the first thing I'm going to do is try to find the area of this rectangle here. What's interesting is that I do know the width of this rectangle, but I don't really know the height or the length of it. And so I'm going to have to figure out what that is. The height of that rectangular area is actually going to be the circumference of the circle, right? If you can imagine, if I folded each of these circles back in and kind of outlined, right, on the outside of this circle, that's going to be the height of my rectangle there, right? If it's the same thing as the outline of my circle. So because my circle has a radius of 5 kilometers, remember that the circumference of a circle is 2 pi r. So I just went ahead and did the circumference there. 2 pi r is going to be 10 pi kilometers squared, or sorry, kilometers. Then the area is just going to be base times height, right? The base is 4, the height, or the circumference of the circle, is 10 pi. So my total area of the rectangle is 40 pi kilometers squared. So I've got this guy covered. Then I just need to find the area of both of those circles, or just find one of them, right, and multiply by 2. So the circle area, we did a lot of those in chapter 10. It's going to be pi r squared. which gives me 25 pi kilometers squared. Then to find the total area, I have to do the rectangle and then do 2 times the circle, or just add circle plus circle. So that is going to give me 40 pi for the rectangle. 2 circles is going to give me 50 pi, right? And add those together, I get a total area of 90 pi kilometers squared. Wouldn't it be nice if there was a shortcut and we didn't have to do all of those little pieces one by one by one? Lucky you, there is a shortcut. So I'm going to show you the formula to find the lateral area of a prism. And remember that the lateral area is this yellow part here, so not including the bases. So the formula for the lateral area of a prism, if you can sort of envision me taking a prism and unfolding it like this, it's going to be the length of the perimeter of the base times the height of the prism. So if you can imagine, here's my base, right, A, B, C, and D. If I unfold the prism, A, B, C, and D, that's kind of like the length of my rectangle there. And then the height of the rectangle is the same as the height of the prism. So the lateral area is equal to the perimeter of the base, so add those guys all together, times the height of the prism right there. And essentially, if I flattened this out, right, if I could iron that out flat for you, that would look like a yellow greenish colored rectangle there. And then you can also have the 2 bases on top and bottom. So then to find the lateral area of a cylinder, which we've already done, but if you can imagine, right, I've got my base on the top and bottom that are both circles, and the height connects the 2 of them. Well, if I sort of turn this into a rectangle like I showed you on that net on the last example, that's actually just the circumference of the base. So our formula is 2 pi r times h, but that's essentially the circumference times the height of the cylinder, right? You could almost still think of this just as the same formula as we had for the prism, which is the perimeter times the height. We just want to be a little more specific because it's a circle that it is actually a circumference. All right, so our final formula, and this is really the most important one of the day, is how to find the total surface area of prisms and cylinders, both. So this is kind of my super simple formula that I like to keep in my mind, is that the surface area is equal to the lateral area, right, around the sides, plus 2 bases. So that kind of works generally whether it's a rectangle or a triangle or a circular base. We find the lateral area, right? So we go kind of around the sides, multiply it by the height. We find that yellow piece or kind of this rectangle in the middle, and then we add on the 2 bases, right? So there should be 2 parallel and congruent bases for every prism or for every cylinder, okay? So lateral area plus 2 bases. So in example 2, we're going to use formulas to find the surface area of each prism rather than having to draw out the net and find individual areas of each individual shape that we have there. So we know that our surface area has to be the lateral area plus 2 bases. The first thing I'm going to always encourage you guys to do in these types of examples is to highlight your bases. Please determine which bases you're looking at first. So looking at this shape, just like we did in our earlier triangular prism, none of the rectangles have congruent and parallel shapes that are opposite from them. So it looks like our triangles are our only option here. So I want to start by finding the lateral area, which is going to be the perimeter times the height of my prism. The perimeter of the base, if you notice, because it's triangle here, I don't have the length of my hypotenuse of my triangle, but this actually is going to be a 3, 4, 5 triangle, right? Because it's a right triangle with side lengths of 3 and 4. Our length must be 5 for the hypotenuse. And you can use the Pythagorean theorem to prove that, or it's a Pythagorean triple. So my perimeter is going to be 13 kilometers. And then the height of the prism, remember, we've got to be careful that the height of the prism connects the 2 bases. The height of the prism is going to be 9 kilometers, right? That 9-kilometer length. So then when I'm trying to find the lateral area, I'm just going to do the perimeter, which is 13, times 9, which is the height, and my lateral area is 117 kilometers squared. Next, I want to find the base area, which we know that the base are these triangles over here. So it's 1/2 base times height is our formula. The base is 4, the height is 3, right? Remember, we want to kind of focus around that right angle there. So that means that my base is going to be 6 kilometers squared. So I'm going to add them together. I have my lateral area plus 2 bases, and that gets me a total of 129 kilometers squared. All right, finally, example 3, we're going to use formulas to find the surface area of this prism again, and this is a cylinder. So the surface area obviously is going to be the lateral area plus 2 bases. First step, highlight your bases. So I clearly have two circular bases here. Notice that 14 is the diameter, so my radius here is going to be 7. So when I find my lateral area, because it's a circle, right, it's a cylinder instead of a prism, I'm going to use 2 pi r to find my circumference or my perimeter of my base and then multiply it by the height. So because my radius is 7, right, the whole diameter is 14, but the radius is 7, and my height is 8, notice that my height connects the two bases here. That looks like I'm going to have a lateral area of 112 pi kilometers squared. And I'm going to leave my answer in terms of pi here. To find the area of the base, because it's a circle, the base area is going to be pi r squared. So this is where a lot of our chapter 10 knowledge is going to come in handy, right? We know that this is a circle, and so we're going to have to use our area of our circle formula that we've worked on in chapter 10. So that's just going to be pi times 7 squared, because 7 is the radius, or 49 pi kilometers squared. And then add them together, I get 112 pi for the lateral area plus 2 circles at 49 pi. That adds together to a total of 210 pi kilometers squared. And I'm going to leave that in terms of pi and not multiply it out. Okay, we are all done finally. We haven't done summaries for a while, but I thought it might be useful for you guys to just do some reflection on your own. If you are interested in doing a summary, my prompt for you is to describe one similarity and one difference between the surface areas of cylinders and prisms. And then for tonight's assignment, you are going to be working on an 11.2 worksheet, which you can find assigned in Teams.